Good day. This demo is going to show you how we can use host-based segment routing to do end-to-end application optimization that results in a beautiful looking graph like the one in front of you. Now, what you're looking at is the graph of response time for an application over time. And we see on the left half of the graph, this is what the performance of the application looks like before turning on our traffic steering. And on the right side of the graph is what our application performance looks like after we've turned on traffic steering. So in terms of response time, over here we have a choppy, inconsistent experience, and over here we have a smooth, much more consistent experience. So we'll get back to this graph in a moment, but let's go through the topology and the use case. So here's the topology we have to demonstrate this use case. We have a network that looks somewhat like you might build a data center where you have, let's say, a top-of-rack switch that goes into your DCI box. That DCI box may have multiple peering connections to go to different providers. Ultimately, those providers lead back to some consumer or some client who's using the application that you're hosting on your server over here on the left. And so as we look at the path that the traffic can take to go from the server over to your client, you see that there are two possible paths, one going through AS1, one going through AS2. And if we just use normal routing, the preferred BGP path may change depending on how policy changes, if routes go up and down, if peering connections go up and down. And what we want to be able to do is protect the traffic going to our client because we value his money and we value his user experience. And so we want to be able to influence which path that takes. And so we're going to do that using a couple of different technologies combined together. One is using segment routing, and specifically egress peer engineering on segment routing to pick a path regardless of what our BGP best path selection takes. And the other one is we're going to use streaming telemetry to determine if we have congestion on any hops between our server and our client, and then adjust the path the traffic takes based on that congestion. And so we're going to do that by, like I said, taking a streaming telemetry from our routing boxes, but also by taking response time statistics and application layer measurement from our remote client. And we're combining those together in, you might call it a controller. I think controller is an overloaded term, so I'm going to call it application path logic. What this really is just an ELK stack. So that's Logstash, Elasticsearch, and Kibana. For aggregating, sorting, and visualizing data. And so we are consolidating those in one place where we then have a very simple script that's a little control loop that is determining what the user experience is, checking if there's any congestion, and then updating the path if needed. And that updated path is being signaled through ExaBGP in the form of an RFC 3107 label stack that gets sent down to our host. And there's a host instance of ExaBGP running on top of a Python library that I've written, which sits on top of the open source VPP project to program those labels into VPP such that traffic that comes from this container, which happens to be running Nginx, a web front end, can then have the appropriate labels selected so it takes the path that we want through the network. Now, let's go back to how this matters. So we say that our BGP path may change depending on which of the external peers we use to get there. Well, using EPE, we have two different ways of getting back to our client. One is if we push label, let's say 24002 onto the packet, and what that indicates to the network devices along the way is basically how to get to the destination. We're effectively using source routing through labels to steer the traffic through the network. So as it comes off of our server, there are two labels pushed onto the packet. The top label is our prefix SID for this peer. And the bottom label is the EPE label that picks either peer 1 or peer 2 for our external connection. So the first hop is going to do a lookup on that first label, and it's going to say, oh, that's going to this peering router. It's going to pop the top label, revealing the EPE label underneath, which then gets sent along to this peering router. He's going to look at the EPE label and say, oh, okay, I'm going to take this top path because I know that's indicated by EPE label 24002. It's also possible there may be a different label put on there. So let's say 24,003. And in that case, same thing, same sequence of steps is going to happen. VPP imposes the label stack. First hop pops the top label. Second hop does a lookup and says, oh, I'm going to the bottom peer, and then pops that label to send it along to its destination. So in this setup, we have a path that can change. We have some background traffic that is randomly changing its path based on changes in the BGP topology. So sometimes it's going across the top, sometimes it's going across the bottom. And then on random time intervals, it'll shift and it'll say, oh, actually now I'm going across the top. Or no, it'll shift and say, now I'm randomly going across the bottom. And the whole purpose of this feedback loop is to detect when that shift is happening and adjust our important traffic to go across the other link. And so if we look at how this ends up being influenced in the graph, this is why we see the behavior we see, because before we turn on any of that traffic steering and my important traffic follows the same path as my unimportant traffic, well, I end up with congestion on my links. And so my response times are kind of all over the place. And in fact, if I drill down on this a little bit more, we'll see that on a shorter time frame, it's actually much worse. And in fact, the duration for which my user experience is bad is actually quite a bit longer. So down here, these are hours. So from, for about a 2-hour period here, my median response time was way above whatever my baseline was. Now, if we go back and look at the right half of the graph instead, sorry, let's go back here. Oops. Now, if we go back and look at the right half of the graph where it's smoothed out, if we actually drill down into, a smaller time frame, we'll see that, yeah, we're actually being pretty consistent. If we drill down into a really small time frame even within that, we will see that, in fact, there are some spikes there, okay? But look at the duration of these spikes. We're talking about maybe 15, 30 seconds maximum. So the message here is not so much that we are preemptively preventing any congestion from ever happening. What we're saying is, by combining the response time statistics with the streaming telemetry and then using that the outcome of that computation to signal an updated path to our host, we're able to dramatically decrease the measurement interval we can use to detect degradation in our application performance and then adjust it. And all of this is being done, just to highlight again, using an open source BGP stack, using open source data plane in VPP, and using what will be an open source Python library sitting on top of VPP that can program labels down. So let's go back to this beautiful graph before I leave you so you get one last glimpse. And I hope you've enjoyed this demonstration, and please let me know if you have any questions. Thanks again.